By the year 1943, a seismic, often brutally sudden, change had swept across the vast, blue theater of the Pacific War. The conflict, once defined by the audacious, seemingly unstoppable advance of the Imperial Japanese war machine, had begun to turn, not with a slow grind, but with a visceral, sickening lurch in the air. The long shadow of Japanese dominance, cast so confidently across the ocean in the war's opening acts, was rapidly receding, replaced by the lengthening, metallic wingspan of American industrial might. This was the year the war in the air, the true determinant of tactical victory and strategic survival, transitioned from a daring raid into a relentless, numbers-driven attrition for which Japan was disastrously unprepared. The crisis manifested most clearly in the decline of an aerial legend, the Mitsubishi A6M0. The twilight of a legend, the Zero's fatal flaw. For 3 triumphant years, the Zero had reigned supreme. It was a fighter born of necessity and innovation, a sleek, almost impossibly light machine that possessed a range and maneuverability previously unheard of in combat aircraft. Japanese pilots, honed by years of pre-war combat in China and imbued with a fierce warrior spirit, had flown the Zero like an extension of their own will. They had decimated Allied air forces across the Philippines, Malaya, and the East Indies, carving out an aerial empire built on speed, agility, and the sheer terror the name Raisen inspired. But 1943 brought an unforgiving clarity to the Zero's design philosophy. Its strengths, its spectacular turning radius and low wing loading, were bought at a terrible, ultimately fatal, cost. The design mandated the stripping away of virtually all protective armor, sacrificing the pilot's safety and the airframe's structural integrity for marginal gains in dogfighting performance. Its fuel tanks lacked the self-sealing capability that was standard on most contemporary Allied fighters. The Zero was, in essence, a porcelain deity of the skies, beautiful, deadly, and shatteringly fragile. As the war matured, the legendary Zero was catastrophically outclassed. The attrition rate was no longer sustainable. A Japanese pilot shot down was a replacement that often took years to train. An American pilot downed was often back in the cockpit within months, or immediately replaced by an endless flow of freshly trained aviators pouring from stateside flight schools. More critically, the new American doctrine had cracked the Zero's turning advantage. Allied pilots learned to avoid the slow, swirling dogfight the Zero excelled at, adopting the boom and zoom tactic, utilizing superior speed, climbing power, and diving ability to attack from high altitude, deliver a devastating burst of heavy machine gun fire, and instantly retreat, never engaging in the Raisen's arena. The Zero's vulnerability to even modest punishment was now its terminal liability. A single, well-placed burst from a heavy-caliber weapon could turn the sleek airframe into a spectacular, flaming pyre. United States: the arrival of the American Leviathans. The shift was personified by the steady, relentless deployment of a new generation of American aircraft, machines built not on the elegance of minimal design, but on the robust principles of speed, toughness, and sheer, overwhelming firepower. The skies over the Solomons and New Guinea suddenly thundered with the presence of these aerial predators. The Allies were fielding faster, tougher, and deadlier fighters, machines built to withstand punishment and deliver it in biblical proportions. Foremost among these formidable newcomers were 2 technological marvels that seemed to Japanese strategists like ghosts haunting the air corridors: the P-38 Lightning and the P-51 Mustang. The fork-tailed devil, the P-38 Lightning. The P-38 Lightning, known ominously to the Japanese as the fork-tailed devil, Naiju-jin, was a twin-engine monster of an aircraft. Its unique configuration, a central nacelle housing the cockpit and concentrated nose armament, flanked by twin booms carrying the engines, gave it unparalleled visibility and climbing power. Crucially, the P-38 was fast, possessing excellent high-altitude performance, and was armored like a tank compared to the Zero. But the P-38's true terror lay in its nose armament: 4.50 caliber machine guns and a 20mm cannon, all firing straight ahead without the convergence issues of wing-mounted weaponry. A P-38 needed only a fraction of a second on target to destroy a Zero. It represented the brutal efficiency of American design: speed to dictate the engagement, armor to survive, and firepower to obliterate. Its appearance signaled the end of the Zero's unchallenged tactical authority in the South Pacific. The purebred predator, the P-51 Mustang. Even more threatening, particularly by the later stages of 1943 when its true potential was unlocked, was the P-51 Mustang. Initially equipped with a serviceable but unremarkable engine, the Mustang became a legend when fitted with the British Rolls-Royce Merlin engine. This synergy transformed the aircraft into arguably the finest piston-engine fighter of the war. The Mustang was sleek, possessing a revolutionary laminar flow wing design that made it breathtakingly fast, far exceeding the Zero's best speed. It could climb and dive with tremendous velocity, and its sheer fuel capacity, especially when augmented by drop tanks, granted it the necessary range to escort American bombers all the way to the Japanese home islands and back. Its presence in the Pacific, increasingly felt through 1943 and into 1944, represented the full maturation of the Allied counteroffensive. It was the ultimate expression of the boom and zoom philosophy, a purebred machine designed to hunt and kill in the high-speed vertical dimension, rendering the agile but slow Zero tactically obsolete. The desperate calculus, a new era of necessity. The consequences of this technological chasm resonated through the Imperial Japanese Navy (IJN) and Army (IJA) air headquarters like a death knell. The once vaunted training pipeline was failing to keep pace with the losses, the industrial capacity to replace airframes was crippled by resource shortages, and, most painfully, the fundamental design principles that had guided Japanese aviation for a decade were suddenly, humiliatingly, irrelevant. The Zero, designed to win the initial, glorious engagements, could not win the grinding, long-term war. The engineers, highly intelligent and deeply patriotic men like Jiro Horikoshi and Takeo Hori, faced an impossible strategic paradox. They had to produce a next-generation fighter instantly, without the industrial base, the materials, or the time necessary to overcome the Allied lead. Every indigenous design they pursued, the heavier, faster replacements for the Zero, was crippled by engine underdevelopment or production bottlenecks. They were designing for yesterday while the enemy was fighting with tomorrow's technology. The radical proposal, the pressure was not just military, but deeply cultural. To admit that Japanese engineering had been outclassed was a profound psychological blow. But the stark reality of the combat reports from Rabaul and Guadalcanal permitted no pride. Survival demanded a bold decision, a move so radical it bordered on technological sacrilege. They would copy America's secret plane, and make it even better. This decision was not born of admiration, but of sheer, unadulterated desperation. It was a strategic imperative predicated on the grim hope of leveling the playing field using the enemy's own weapons against him. To obtain true parity, speed, armor, and firepower, in the limited timeframe remaining, the Japanese had to bypass the arduous, time-consuming process of original engine and airframe development. They had to reverse engineer the most sophisticated, devastating technology the enemy possessed. This realization, that the only path to regaining air superiority was through the appropriation of the very designs that were slaughtering their pilots, set the stage for one of the most secret and audacious technological gambits of the entire war. The Imperial engineers were ready to cannibalize their own traditions, scour the wreckage of crashed American planes for their secrets, and stake the fate of their nation on a desperate, high-stakes race to the sky. The decision to abandon pure indigenous development for a rapid, technologically parasitic approach was revolutionary for the proud, often insular world of Japanese military engineering. This wasn't merely imitation, it was an act of national survival, a desperate gambit to buy time against an enemy whose industrial and technological curve was escalating exponentially. The second phase of this desperate race for the sky began in the wreckage and the shadows. The target, unmasking the engine's heart. The Japanese engineers, primarily within the Army's Technical Air Division, understood the core of the Allied advantage was not solely the airframe, but the power plant. The Zero's engines, while light and reliable, simply could not deliver the sustained horsepower, reliability, and high-altitude performance of the latest American designs. They initially coveted the engine that powered both the early P-51 Mustangs and the formidable P-47 Thunderbolts, the Pratt & Whitney R-2800 Double Wasp. This massive, 18-cylinder radial engine delivered well over 2,000 horsepower and was the epitome of rugged American engineering. Its durability and power were legendary, allowing Allied fighters to soak up damage and still return home, something unthinkable for the fragile, air-cooled engines of the Imperial forces. However, the R-2800 was a massive, complex, and distinctively American design, featuring production tolerances, materials, and supercharging technology far beyond immediate Japanese replication. The sheer scale and complexity of its manufacturing process made an instant copy impossible, especially given Japan's dwindling strategic material reserves. The revelation. The Allison engine. The focus soon shifted to a more accessible, and perhaps more replicable, target. Prior to the adoption of the Rolls-Royce Merlin engine, many early P-38 Lightnings and P-51 Mustangs were powered by the Allison V1710 liquid-cooled V12 engine. It was this engine, or rather, the advanced versions found in captured or recovered wreckage, that became the Holy Grail. The Allison was still a potent, high-horsepower engine, and its V12, liquid-cooled configuration was more familiar to Japanese engineers who had experimented with similar layouts, even if their attempts were never successfully mass-produced. The discovery of a relatively intact Allison engine, likely scavenged from a downed P-38 or an early P-51 in the fierce fighting over New Guinea or the China-Burma-India theater, was treated as a treasure of almost immeasurable value. Project Boro. The clandestine lab. The process of deconstruction and analysis was immediately elevated to a national priority, code-named Project Boro, pillaged loot, by some involved circles, reflecting the nature of its origins. The engine was transported under extreme secrecy to one of the Army's most secure research facilities, possibly near Tachikawa or a secluded lab within the Nakajima Aircraft Company. There, shielded from bombing raids and spying eyes, an elite team of engineers and metallurgists began the painstaking, millimeter-by-millimeter dissection of the captured unit. Reverse engineering the mechanics. Components were measured with meticulous precision. Every gear ratio, valve timing, and cylinder tolerance was documented. The V1710's complexity lay not just in its assembly, but in its supercharger system, a multi-stage unit that allowed it to maintain power output even at extremely high altitudes, precisely where the Zero's engines faltered. This system became the primary focus of the mechanical reverse engineering effort. The metallurgy challenge. The deepest, most insurmountable challenge was often metallurgical. The high-stress components of the Allison engine, the cylinder heads, pistons, and crankshaft, were made from specialized, high-grade alloys that Japan simply could not reliably reproduce. The Americans had access to abundant nickel, chromium, and vanadium. Japan did not. The Japanese metallurgists spent agonizing months attempting to identify the exact composition and heat treatment processes, knowing that any compromise in materials would lead to catastrophic engine failure in combat. The blueprint from wreckage. The engineers worked not from blueprints, but from fragments. Dented crankcases, warped cooling systems, and burnt wiring were their primary source documents. This forced a level of deduction and assumption that carried immense risk, transforming the engineering project into a high-stakes detective investigation. The Japanese, Lightning, the Key 83 concept. As the engine analysis proceeded, a parallel effort was launched to design an airframe capable of housing this powerful new engine, or its Japanese copy. The Army settled on a heavy, twin-engine fighter concept, consciously mimicking the P-38 Lightning's high-speed, high-altitude interception role. This design materialized as the Kawasaki Ki-83 concept, and later, other, similar high-speed interceptors. It was envisioned as a long-range, heavily armed fighter, prioritizing speed and altitude over the maneuverability that had defined the Zero. The specifications were a wish list born of necessity: a top speed near 700 km per hour, a strong airframe, and concentrated nose armament, echoing the P-38's destructive punch. The goal was clear: to create an aircraft that, when finally fitted with the cloned American engine, could meet the P-38 and the P-51 on equal, if not superior, terms. It was a race against time, scarcity, and the inherent difficulties of reproducing a complex, high-performance technology under siege. Failure meant the uncontested reign of the Allied fighters, leading inevitably to the strategic bombing and total defeat of the home islands. The laboratory floor smelled of scorched metal, petroleum residue, and the acrid tang of human desperation. Under the harsh, bare electric lamps, the pristine elegance of the Zero's design philosophy seemed a distant memory. Here, in the sealed, secure workshop, far from the chaos of the front lines, the future of Japanese airpower was being painstakingly reconstructed from the fragmented ruins of its enemy. This was the dark, analytical heart of Project Boro's second stage, the true operationalization of the plan to copy America's secret plane. The anatomy of the enemy. The captured American airframe are carefully collected pieces of multiple wrecks, lay splayed across heavy wooden tables like the dissected remains of a fallen colossus. The engineers, highly disciplined and intensely focused, approached the task with an almost religious fervor. Japanese engineers carefully disassembled the wreckage. This was not just a stripping of parts, it was a meticulous archaeological excavation of an advanced technological civilization. Every rivet, every structural joint, every piece of internal wiring and tubing was catalogued, photographed, and compared against Japanese standards. The wiring loom. They were immediately struck by the sheer redundancy and robustness of the American systems. Where Japanese aircraft often used delicate, weight-saving wiring, the Allied planes utilized thick, heavily insulated cables, a small detail that underscored the vast difference in philosophy between lightness and survivability. The hydraulic heart. Every bolt, cable, and hydraulic line was studied. The hydraulic systems, which powered everything from the landing gear to the massive flaps and potentially heavy-caliber gun mechanisms, were far more potent than anything in a Zero. This robust power was essential for high-speed maneuvering and operating the heavier airframe needed to carry armor and superior firepower. The complexity suggested manufacturing tolerances that were frighteningly high, tolerances Japan's war-battered machinery struggled to maintain even for simpler components. The secrecy of self-sealing. The fuel tanks were a subject of particular fascination and frustration. Japanese tanks were simple aluminum containers, the American ones were elaborate, self-sealing bladders, layered with rubber and fabric designed to swell in close bullet holes almost instantly. The rubber compounds used were unique, relying on vast, stable supply chains of raw materials that Japan could no longer access. This single detail represented the insurmountable material advantage of the Allies. The blueprint for a savior. The accumulation of this salvaged intelligence led the design teams, spearheaded by engineers from the Army's technical bureaus, to solidify the plan, build Japan's own twin-engine, high-altitude interceptor, inspired by the Lightning. The P-38 Lightning provided the perfect template for a Japanese countermeasure. Its configuration offered the crucial combination of a high power-to-weight ratio due to two engines' excellent high-altitude performance, and a concentrated nose armament capable of shredding American bombers and heavily armored fighters. This concept crystallized into several parallel, desperate projects, but one primary high-speed test bed captured the imagination. They called it the Tachikawa Ki-78 project, or later, the Shinzen concept. While the Ki-78 was initially conceived as a high-speed research aircraft, it embodied the core ambition, achieving speeds that could only be attained by embracing the twin-engine, aerodynamic principles observed in Allied designs. The Shinzen Deep Mountain concept aimed for altitude and speed, a plane that could lurk above the fighting, ready to dive like a hawk onto incoming formations. However, even as the scale models were being carved and the first blueprints inked, the grim reality of the situation began to erode the audacious dream. But the dream was already showing cracks. The cracks were not merely theoretical, they were structural, material, and strategic. The grand design of an indigenous Japanese Lightning collided violently with the brutal material realities of late-war Japan. The engineers were attempting to build a 1944 specification machine using 1939 level manufacturing capacity, while enduring 1945 level scarcity. The grinding halt of industry. The primary enemy was no longer the P-38 pilot, but the relentless pressure on the home island's infrastructure. Japan's factories were under constant bombardment. B-29 superfortresses, now operating from captured Pacific bases, were systematically destroying the very industrial complexes needed to forge the new Savior aircraft. The air raid sirens became a constant feature of the engineers' lives, often sending them scrambling into shelters while irreplaceable machine tools sat idle. This disruption shattered production schedules and further degraded the already low-quality control standards. The material shortage was catastrophic. Aluminum was scarce, engines unreliable, and precision tools almost non-existent. The aluminum famine. Aluminum, the lifeblood of aircraft construction, was rationed severely. Engineers were forced to substitute steel or even wood in non-critical areas, adding unacceptable weight and complexity to designs intended for high performance. The choice was between a heavy, slow aircraft or no aircraft at all. The engine deficit. The original copycat engine, the Japanese, Allison, faced insurmountable hurdles. While the V-1710 was understood, reproducing it reliably was impossible. Lacking high-quality alloys, Japanese versions suffered from poor piston rings, rapid overheating, and abysmal service lives. They delivered their rated horsepower only briefly, if at all, and often failed catastrophically after minimal operational hours. The goal of making it even better devolved into a desperate plea to simply make it work. The turbocharger wall, the most critical and most impenetrable barrier to true parity, was the turbo supercharger. This component was the heart of the P-38's high-altitude performance, utilizing exhaust gases to compress the thin air, allowing the engine to breathe normally at extreme heights. The P-38's complex turbo superchargers were impossible to replicate. They relied on precision metallurgy for their high-stress, high-temperature turbines, demanding materials that could withstand immense heat and rotational speeds without warping or failing. Japan lacked the necessary nickel alloys and the specialized forging techniques. The failure to copy the turbo supercharger meant that even if the engineers could build a robust V12 engine, its performance would drop off dramatically above 20,000 feet, exactly where the American bombers and the P-38s liked to operate. The Japanese interceptor would be crippled at the altitude where it was most needed. The patchwork imitation. Still, engineers pressed on, improvising with what they had. This improvisation was a testament to the dedication and ingenuity of the Japanese technical corps, but it also became the ultimate weakness of the final product. The desperation forced compromises in every aspect of the design. Simplification of systems. Complex hydraulic and electrical systems were simplified, often reducing reliability and operational capability to speed up production. Armament downgrades. Plans for heavy cannon armament had to be scaled back due to weight and recoil concerns in the improvised airframes. Aero compromises. The clean lines and optimized aerodynamics of the original American designs were often spoiled by hasty, rough-hewn production techniques. What emerged from this crucible of scarcity and ingenuity was more a patchwork imitation than a true copy. It was the embodiment of a nation trying to leapfrog a decade of industrial progress in a single year, while under constant siege. The resultant Japanese aircraft, the Ki-83, the Ki-98, and other desperate high-speed interceptor projects, were brilliant designs on paper, but in reality, they were often hamstrung by unreliable power plants, inferior materials, and a lack of necessary high-altitude boosting. They were late war masterpieces of engineering, but ultimate victims of a lost industrial war. The dream of a superior Japanese Lightning had become a phantom, a symbol of what could have been, perpetually grounded by the crushing weight of strategic attrition. The culmination of Project Boro, the frantic dissection of Allied wreckage, the desperate calculations, and the cultural leap to imitation, was the unveiling of the prototype. After months of working in secrecy and under constant strain, the engineers and ground crew at the test facility finally saw the fruit of their sacrifice. This new aircraft, a synthesis of scavenged secrets and indigenous grit, was meant to be Japan's final, powerful countermeasure. The appearance of salvation. When the prototype finally rolled out, it looked impressive, sleek, modern, powerful. The specific models varied, whether it was a high-speed interceptor like the Kawasaki Ki-83 or a design influenced by the lessons of the P-38 like the proposed twin-boom fighters. The visual impression was a stunning departure from the delicate Zero. This was a heavy fighter, a machine built for speed and altitude, its long, laminar flow wings speaking of high velocity, its twin-engine nacelles suggesting immense power. The metallic skin, perhaps painted in a hastily applied, dark green camouflage, reflected the last vestiges of Japan's diminishing industrial prowess. For the watching military observers, the stern-faced generals and the weary naval commanders, the rollout was a moment of profound, almost religious anticipation. They saw not a mere aircraft, but the Shinzen Deep Mountain, the projected savior that would push the B-29s out of range and allow the Zero pilots to survive another day. The aircraft looked like a match for the American behemoths, promising the speed and durability that had been fatally absent in the Zero. The truth of the maiden flight. The first test pilot, a veteran of the long, grinding campaigns in the South Pacific, strapped into the cockpit. He was a man accustomed to the responsive, light handling of the Zero, and he approached this heavy, complex machine with professional caution, yet tempered by a fervent national hope. The twin engines roared to life, their sound different, deeper, and more forceful than the familiar radial thump of a standard Japanese fighter. The plane lumbered down the runway and lifted off with a power that thrilled the onlookers. But the first test flight told a different story. The pilot's radio transmissions soon began to paint a picture of mechanical protest and aerodynamic descent. The sheer speed and power, which looked so impressive on paper, translated into an unpredictable beast in the air. Aerodynamic discord. It was unstable. The complex, high-speed aerodynamic design, copied without the benefit of America's advanced wind tunnels and computer modeling, suffered from unexpected parasitic drag and control surface flutter at high speeds. The controls, though hydraulic-assisted, felt heavy and unresponsive compared to the Agile Zero, making the micro-corrections necessary for sustained combat impossible. The engine's fatal flaw. Most critically, the Japanese Allison, the reverse-engineered engine, revealed its lethal flaws almost instantly. Engines overheated, lacking the pure, high-nickel alloys and the sophisticated cooling systems of the genuine American article. The Japanese copies could not handle sustained high-power output. Piston rings failed, cylinder heads warped, and temperatures soared past critical limits, often after just minutes of full throttle. The high-altitude potential, dependent on an unreplicated turbo supercharger, simply did not materialize. The dream's collapse. The debriefing was a somber, devastating affair. The data loggers confirmed the pilot's grim report. Performance was far below expectations. The top speed, projected to match or exceed the P-38, was hundreds of kilometers per hour short. The rate of climb, necessary to intercept high-flying bombers, was sluggish. The operational ceiling was drastically limited. The American P-38 was a holistic system, a perfect marriage of a robust engine, sophisticated supercharging, and a carefully balanced airframe. The Japanese attempt was a forced, fractured marriage, a temperamental engine shackled to a promising but flawed airframe, all built with inferior, substitute materials. The collective realization hung heavy in the hangar air. The dream of matching America's air power was slipping away. The technological chasm was too vast, the industrial momentum of the Allies too powerful, to be bridged by even the most brilliant act of espionage and reverse engineering. The disappointment of the test flights did not lead to surrender, but rather to a furious, desperate surge of remedial work. The engineers were not just fighting a war, they were fighting the laws of physics and the brutal economics of scarcity. Fighting the inevitable. Inside Japan's hangars, engineers fought a losing battle. The Tachikawa and Kawasaki facilities became round-the-clock battlegrounds against the limitations of their own resources. Teams slept beside their drafting tables, fueled by thin tea and fierce patriotism. Every failure of the prototype demanded a redesign, a modification, and a fresh attempt to coerce the unreliable machine into the required performance envelope. The endless redesign cycle. They redesigned wings, reinforced the frame, and tweaked the engines, but nothing worked. They tried different propeller pitches, adjusted the cooling scoops, and added extra oil radiators, hoping to tame the engine's internal fire. They structurally reinforced the airframe to handle the unexpected vibrations and stresses, adding necessary weight that further degraded performance. Every modification was a compromise, a trade-off that chipped away at the initial promise of high speed and agility. The incooperative systems. The copied components themselves seemed to possess a stubborn, almost sentient resistance to Japanese integration. The copied systems refused to cooperate. The complex, high-pressure hydraulics, perfectly manufactured in the US, were leaky and unreliable when made with substitute Japanese seals and lower-grade tubing. The sophisticated landing gear mechanisms, designed to fold neatly and robustly into the twin booms on designs like the Ki-83, often jammed or collapsed, products of imprecise machining and material weakness. The fatal deficit. Data and materials. The core problem was not the talent of the engineers, which was immense, but the lack of foundational data and materials. Reverse engineering a complex modern fighter is not just about copying shapes, it's about understanding the specific data that informed those shapes. Stress tolerances, airflow characteristics, heat dissipation rates, and the precise metallurgical composition required for a component to survive high-G maneuvers. Japan had none of the necessary data, forcing them to rely on trial and error, a process too slow for a war that was already rushing toward its conclusion. Without proper materials and data, Japan's imitation turned into a nightmare. The material shortage was the final, insurmountable nail in the coffin. High-performance aviation engines demand specific, heat-resistant alloys. Japan's inability to produce high-grade nickel steel for the crankshafts or chrome vanadium for the cylinder heads ensured that the life expectancy of their American engine copy would always be measured in tens of hours, not hundreds. They were creating high-performance fighters that would fail spectacularly in the air, not under enemy fire, but under the stress of their own operation. By late 1944, as the prototypes either crashed, languished in endless modification cycles, or barely achieved marginal flight performance, the dream of a new generation savior fighter faded entirely. The grand, audacious plan to steal the enemy's technology and turn it against him had succeeded only in producing a fleet of phantom fighters, brilliant blueprints and promising airframes tragically compromised by the overwhelming industrial and material superiority of the United States. The race for the sky was lost, not in the air, but on the factory floor and in the metallurgist's lab. The sunset of an empire. By the time the Japanese Lightning was almost functional, the war had already turned hopeless. The development cycle, complicated by reverse engineering challenges and crippling material shortages, ensured that the first flight-worthy prototypes of aircraft like the Kawasaki Ki-83, perhaps the closest realization of the twin-engine dream, arrived far too late. By late 1944 and early 1945, the tactical situation had deteriorated past the point where a single, albeit capable, interceptor could turn the tide. The air war had entered its final, brutal phase. American B-29s ruled the skies. These massive superfortresses, flying above 30,000 feet, were simply unreachable and unpunishable by the bulk of Japan's remaining air defenses. They systematically flattened the industrial base needed to mass-produce the very fighter designed to stop them. Japan's few remaining frontline fighters, still predominantly aging Zeros or marginally improved interceptors like the Ki-61 Hine Tony, were either too slow, too fragile, or lacked the necessary altitude performance to engage the B-29s effectively. The nation was starving. Japan's resources were gone, and the copied plane never saw real combat. Every gallon of high-octane aviation fuel was a painful sacrifice. Every sheet of high-grade aluminum was a commodity more valuable than gold. The decision was made, repeatedly, to preserve the few successful prototypes, shielding them from the desperate operational commanders who would surely have flown them to certain, swift destruction. These last, precious examples of technological endeavor were too important as symbols of future hope, or too unreliable for actual combat, to be risked. The Ki-83, capable in its test flights but chronically dependent on scarce materials and high maintenance, and other desperate projects like the high-speed Nakajima Ki-87 high-altitude interceptor, became relics before they were even operational. It remained a symbol of desperation, hidden in a hangar as the empire fell. These gleaming, powerful machines, the ultimate expression of the desperate gamble to copy the enemy, were grounded, silent witnesses to the devastation unfolding overhead. They were magnificent phantom fighters of a war already lost, destined to be captured by the very enemy they were designed to fight. The sudden, bewildering end of the war in August 1945 brought an immediate cessation of hostilities and the arrival of Allied technical intelligence teams. Their mission was to scour Japan's factories, airfields, and research labs for the secrets of their former enemy. They were particularly interested in the late war, high-speed interceptor designs. They had heard rumors of planes designed to shoot down the B-29. Shock and sardonic amusement. After Japan's surrender, Allied investigators examined the failed prototype. They found the hangars not filled with mass-produced squadrons, but with single, exquisite prototypes, often in advanced stages of testing or final assembly. Among these prizes were the twin-engine speedsters, clearly inspired by the success of the P-38. The initial inspection led to immediate shock and amusement. The external examination revealed a stunning degree of fidelity. The engineers had successfully replicated the aerodynamic shape, the sleek lines, and the overall powerful posture of a modern American fighter. The plane was a near-perfect visual copy, but inside, it was chaos. The true story of the Shenzhen project unfolded under the scrutiny of trained Allied eyes, experts who understood the difference between cosmetic appearance and functional engineering integrity. The interior chaos. As panels were removed and systems inspected, the investigators saw the tragic evidence of the material shortage. Components meant to be manufactured with micro-tolerances were often visibly misaligned. Critical structural joints showed evidence of crude welding, the hasty work of desperate technicians forced to use manual processes due to the destruction of automated tools. The compromised power plant. The core failure lay, as expected, in the engine bays. The Japanese V-12 engines were powerful but fatally compromised. Their reliance on inferior, low-alloy steel and aluminum meant that performance metrics were based on brief, non-sustainable bursts of power. The absence of the critical turbo supercharger units, the hallmark of American high-altitude dominance, was obvious. The weak power plants told the full story of a nation defeated by industrial attrition before the bomber formations even arrived. The conclusion was undeniable and delivered with a sardonic finality. Japan had tried to duplicate America's masterpiece, and failed spectacularly. It was a failure born not of a lack of skill or intelligence among the engineers, but a total collapse of the supporting industrial ecosystem, a system that could produce 1 million rivets and high-grade alloys consistently. The prototype was a hollow shell, a monument to the ultimate strategic reality that in modern warfare, the victory belongs to the side with the deepest, most resilient manufacturing base. The captured Japanese prototypes were packed into crates and shipped to the United States for full technical evaluation, forming a crucial coda to the history of World War II aviation. Today, the saga of the Japanese copycat fighters endures as one of the most compelling human and technological stories of the war's final phase. Today, the project stands as a fascinating footnote of World War II aviation history. It is a narrative less about aerial combat and more about the global industrial race that ultimately decided the conflict. The contrast between the Japanese methods and the American outcome perfectly summarizes the entirety of the Pacific Air War. The limits of genius. The effort showed how far Japan was willing to go, to swallow its pride, abandon its traditions, and commit to the risky, desperate strategy of technological parasitism. It confirmed the immense talent and dedication of the Japanese engineering corps, who accomplished miracles with the meager resources available. The unbridgeable gap. Simultaneously, it dramatically revealed how far behind it had fallen. The failure was not one of imagination, but one of logistics. The engineers could design the aircraft, but the nation could no longer build it to the required standard. The American and Japanese approaches stand in stark historical juxtaposition. Innovation built the P-38. It was the result of a stable design process, endless access to high-grade materials, massive investment in R&D, and the ability to produce tens of thousands of reliable engines. It was a product of confidence. Desperation built its imitation. It was the result of a nation facing annihilation, forced to cannibalize its enemy's wreckage and compromise every standard of quality simply to survive. It was a product of fear. And in that contrast, you can see the entire story of the Pacific Air War. It was a conflict decided not by the skill of individual pilots, nor the beauty of a single design like the Zero, but by the overwhelming, industrial force that could consistently field faster, tougher, and deadlier machines, allowing them to win the race for the sky long before the final prototypes of the Japanese Lightning ever left the ground.